I want to thank the organizers to give me an opportunity to give this talk here today. This talk is mainly based on a review paper that I wrote for annual reviews, and the details of the paper is given here. So I'll be talking about different convergence diagnostic measures for MCMC. So here's the problem. The problem is that we have a non-negative function on, say, d-dimensional Euclidean space, which we know is integrable, but we do not know its integral. Okay, so we can, given this non-negative function and given the fact that it is integrable, we can define the density function pi, which is the normalized, the function u, and then this is our target density. This pi is our target density for the talk today, and different features of pi that we might be interested in are often can often be expressed as a means of certain functions with respect to pi. So, for example, by changing g, you can get the location measures for pi, the spread measures for pi, right? And which are, so the integral with respect to pi is then simply the integral, it's a ratio of two integrals, right? The numerator is the integral of g times u, the product, and the denominator is obviously the normalizing constant that makes pi the density, the probability density. And so we want to evaluate this integral, but unfortunately, in most of the practical problems, this is intractable. This expectation is intractable because both the numerators and denominators are intractable, right? So we often deals with, for example, in Bayesian context of posterior density, which is known only up to a normalizing constant. So we know the u, the functional form, but we do not know the normalizing constant, right? And we want, say, posterior means of some function g. Now, there are different ways of approximating this integral, right? And today we will be talking about Monte Carlo methods. The classical Monte Carlo method, the ordinary Monte Carlo method, is that if you can sample from pi, then you get samples, those samples, the IID samples, to form what is known as the sample mean estimator, the sample averages, which I'm denoting by G and bar, and you can use that sample average to estimate the mean, the population mean, the expectation E pi G that we want. And the justification here here comes from the laws of large numbers, which says that if you have large enough sample, then the sample mean is close to the population mean, right? And not only that, if you have a central limit theorem, and you know that if G has finite second moment, there is a central limit theorem, and you can estimate that population variance lambda G square by the sample variance, right? And you can use this sample variance to construct what is known a confidence interval for the population mean expectation of G. And in fact, a 95% confidence interval will be, centered at the sample mean G and bird minus plus this, this score 1.96 times the standard error SG over square root n, where SG is the sample standard deviation. Now, this confidence interval can be used to do the standard sample size calculations to determine what is an appropriate sample size, right? How many samples do I need to collect, right? So in fact, we, based on a pilot sample, we can calculate, an estimate of the variance. That is, we can calculate SG, and then we can calculate the width of this confidence interval, right? And if that width is deemed too high, then we can do this sample size calculation to determine what is an appropriate sample size you need to achieve a desired level of precision, desired level of accuracy. So that's how we choose the sample size. Okay, so this is the classical Monte Carlo method. Now, so we have the same problem, right? We want to estimate these mean. We want to estimate this mean, and we want to estimate this mean. And we know the classical Monte Carlo method is get IID sample from pi to form these sample averages. But most of the time, the problems that we are dealing with these days, it's not computationally efficient to get IID sample. So there is no computational efficient computational method to get direct sample from pi. Well, this is where the Markov chain Monte Carlo methods can help. What Markov chain Monte Carlo method says that instead of IID samples, if you can run a Markov chain which has this pi, remember the target density pi as its stationary density, and is appropriately irreducible. Basically, it can explore the state space, from anywhere. It can go anywhere with positive probability. Then you can run. You can use these samples, the MCMC samples, to construct what is known as the sample average, or the time average estimator. Basically, the same GN bar, right? You just replace the IID samples by these Markov chain samples. And there is a Markov chain strong law of large number which says that, well, no matter where you start, right, X0 is the initial distribution, that is where you start the Markov chain, and then this Markov chain needs the initial distribution and that one-step mechanism, right? Given the current, how do you move to the next? So, the Markov chain strong law of large number says that no matter where you start, no matter what is the initial distribution, it's not, the sample average converges to the population mean. Okay, so sample mean goes to the population mean. That's one convergence we're talking about, right? The summary statistics converges. Also, it can be shown that, under standard conditions, I mean, if you denote the marginal distribution of Xn, the nth iteration of your Markov chain, the marginal distribution of Xn converges to the target pi. Okay, so Xn converges to the stationary distribution pi. But no matter where you start, no matter what is the initial value X0, X0, you can start from a distribution, or you can start at a fixed value, that is a degenerate distribution, so you can start anywhere. But obviously, if you start far away from the target, far away from the stationary distribution, it will take longer to be closer to the target, right? So yes, the initial distribution has an effect in terms of how long it takes to reach pi. No, so this is the concept related to what is known as burn-in. So the question is, where do I start? I mean, when I say that where do I start, I mean, I'm saying where do I start collecting samples from, as opposed to where do I initialize, that is X0. Now, so, obviously you would like to start where, when your Xn is close to pi, right? So that is what I'm discussing in the next slide. So where do I start collecting samples and when to stop? Well, we know that Xn converges to pi, right? We know that it converges to the stationary distribution as n tends to infinity, as you collect more and more samples, as you run your Markov chains longer and longer. And we also know that the summary statistics converge to the population means, the population summaries. Now, so since we know that the Fnx converges to pi, so if we find the smallest n prime such that the distance between Fn and pi is less than 0.01 at n prime, and obviously for any subsequent n, that it will be still smaller than 0.01, because these distances converge going down to 0. So then we can say that by n prime iterations, the chain has approximately reached stationarity. So this n prime is referred to as the honest choice of burning. Okay. Now this cutoff point 0.01 is arbitrary. Any other small value can be used. So there is a half in my this distance set in the left side, because that is basically what is the total variation distance between xn and the target, right? Now, so obviously it turns out that most of the Markov chains that we are running and most of the pi that we are dealing with, we know that pi is intractable. This total variation distance is not available in closed form. So you just can't do this for most of the practical problems. And but there are methods of constructing a quantitative upper bound to the total variation norm, and on the left hand side, the total variation distance. So then we can make sure that the upper bound is small. Okay, so that is a choice. That is a method we can use to find out about an appropriate bounding value. Now, so that's where we can start collecting samples. Now, when to stop, that is related to the sample size calculations that we did for IID case. So in particular, if there is a central limit theorem, right, starting at n prime, right? Now, if there is a central limit theorem, and if you can estimate that asymptotic variance sigma g square in the CLT, then you can form a confidence interval, right? And then we can use the same kind of method, the sample size calculation method we use to determine an appropriate n, right? Now, so there are a couple of problems here. The one is, this asymptotic variance in the CLT, which I am denoting by sigma g square. As you can see, it is not same as lambda g square, the population variance, right? Because these are Markov chains, so the samples are correlated, the serially correlated. So there will be this auto covariances that you need to take care of. Now, so there are a couple of problems. One is, just as in the classical central limit theorem, we saw that just finite second moment guarantees that. It turns out that for Markov chain, that's not the case. So you have to make sure that your Markov chain is mixing well. Mixing well means it is exploring the target space well, it is moving quickly. So then, these central limit theorem holds. But then once you have that, you can do the sample size calculation that we generally do in ordinary Monte Carlo to determine an appropriate sample size, to determine when to stop, right? So now we have discussed where to start and when to stop. Now, so indeed, that is what lead to what is known as the fixed width stopping rule, where it's epsilon is a predetermined threshold, say 0.005. And you stop your simulation, you terminate your simulation when the half width of the confidence interval, like T star is an appropriate quantile, the half width of the confidence interval is below that threshold, right? So that is the fixed width stopping rule. Now there are variations to this fixed width stopping rule known as relative fixed width stopping rules. Now, in particular, in these cases, where you are you want to make sure that your Monte Carlo uncertainty, the Monte Carlo error, is smaller compared to the standard error, the standard deviations of the population distribution. The posterior, for example, in the Bayesian world, the posterior standard deviation. Now, so that gives you to the relative standard deviation fixed width stopping rules. So there are other, like the relative magnitude stopping rules, so on and so forth. Now, a related concept is the effective sample size. So since Markov chain results in a correlated sample, you want to know, so I have these correlated dependent samples, how many IID samples is equivalent to my Markov chain samples, right, in terms of having the same standard errors. So in fact, the effective sample size is defined as n lambda g square. Remember, lambda g square is the population variance divided by the sigma g square, that's the Monte Carlo the variance. And it turns out this relative standard deviation stopping rule, fixed width stopping rule, is equivalent to saying that we would like to have enough effective sample size. Okay, we have to have enough effective samples. So these are equivalent. These are equivalent. Now there are many other diagnostics. So the most popular is definitely the Gelman-Rubin diagnostic, the R hat, the potential scale reduction factor, where you start multiple, the parallel chains, multiple chains, started at what they call what is known as the over dispersed value, so well separated, with respect to the target distributions. And then when you run these chains, then you compare the within variance to the pooled variance based on these chains. So then there is a Guecki statistic, the Heidelberg and the Welch statistic, Raftery and Lewis diagnostic. So these methods are based on either moments or the spectral density methods. There are also methods based on kernel density. So you compare the kernel density based on your Markov chain samples. And obviously, there are popular graphical tools that we use. The most popular maybe the trace plots and the autocorrelations plots. So trace plot is a time series plots where you are plotting the realizations against the iterations, and the autocorrelation functions is plotting the lag k autocorrelations as the lag increases. Now, so we in the review paper we have discussed all these different methods, reviewed all these methods for as potential tools for Markov chain convergence diagnostics. Now, for the sake of time, I'm going to talk about some examples now. The first example is a very simple target distribution, is the exponential with rate parameter 1. Now, consider an independence metropolis sampler to explore this target distribution. With the independence metropolis sampler with exponential theta proposal. Now, it can be shown that if this theta in the proposal distribution is less than 1, then the total variation norm between Fn, remember Fn is the between Xn, the distribution of Xn, the marginal distribution of Xn, and the target density is bounded above by 1 minus theta to the power n. So in particular, if I take the independence chain with theta equal to 0.5, then n prime, my honest choice of burn-in will be 7. So 7 iterations. Okay. Now 7 iterations where we can start collecting samples. So we ran 2 independence metropolis chains for 1000 iterations. One chain with theta equal to 0.5, that's my top row, and then the bottom row is theta equal to 5. Now, as you can see, and these chains are started at 0.1, starting at the initial value, a deterministic value, 0.1. Now, you can see from the trace plot in the top row, it is, it's mixing pretty well. And the autocorrelations are also dying down very fast. Whereas when theta is equal to 5, you can see that the trace plot, there are a lot of flat beads, which is basically saying that it is suffering from slow mixing. That is, it's not exploring the state space quick enough, and the reason is when theta is equal to 5, the proposal, the tail of the proposal distribution is much lighter than the target, so it doesn't make large move, and whenever it makes a large move, as you can see, it gets rejected. So it so there is this flat beads, right? And also you can see that the slow mixing is also corroborated from having that autocorrelation plot because it has large autocorrelation values, right? Now, so from the top plot, we can see that is for theta equal to 0.5. We don't need a burn-in. We can actually start from the first iteration itself. Whereas from the second row plot, we can see that you need to run the chain longer because it is suffering from slow mixing. It has not reached stationarity yet. Now, so in the paper we also use all other methods that I discussed in the previous slides. In this case, but for the sake of time, and let me move on to now the concept of choosing when to stop simulation, right? When to stop simulation. Now, suppose I want to estimate the mean of the target distribution. So if I use the fixed width stopping rule, and suppose I want the cutoff to be 0.005, then we can see that starting at x8, because 7 was my burn-in value, I need n star, which I am denoting as the sample size, to be a little over 323,000 iterations. And if I use ESS, the effective sample size criterion, then I need, so with the same cutoff, I need 153,658 iterations. Remember, effective sample size criterion is equivalent to the relative standard deviation fixed width stepping rule. Now, suppose, so here is the what is called the mean plot. So I'm plotting the sample means against the iterations for that 323,700, I think, iterations. As you can see, for the left plot is for theta equal to 0.5 chain. So it has, and the horizontal line is the target 1. So it has reached quite early. Whereas for the theta equal to 5 chain, even after 323,700 iterations, the mean, the sample mean estimate is quite far off from the target. Obviously, in practice, we don't know the true value, so we can't do that. Now, I also used the Gelman-Rubin diagnostic, the PSRF R hat plot. Now, the left plot again is for theta equal to 0.5. The right plot is for theta equal to 5. So we started again at multiple parallel chains, started at different starting values. So you can see from the left plot, it has reached the cutoff. So 1.1 is a standard cutoff for R hat that is used pretty early. In fact, by 100 iterations, you can see that the PSRF reaches below 1.1. Now, if we use 100 simulation, we can see that the standard error is still pretty large. So the PSRF actually in this example is leading to a premature termination of the chain. Okay. Whereas for theta equal to 5 chain is, it's even after 2,000 iterations, as you can see that, the PSRF factor is quite high. So it's basically saying that there is a convergence issue going on. Now, let me move to another example. In this example, I have a multimodal target. And in fact, I plotted the marginal density of X, which is unimodal, but it's a bivariate example. The marginal density of Y, as you can see, has 6 modes. Now, in this example, again, so here I'm just considering the convergence to stationarity. So the burn-in question here, right, instead of the convergence of the summary statistics here. Now, so what we do is we consider 2 cases. In the first case, so we start 4 parallel chains at, so 4 parallel chains out of which 2 at one mode and 2 in another mode. Okay, and I plot the trace plots, the trace plots for the X marginals of the 4 chains for the last 1,000 iterations of these 3,000 iterations is seen in the left plot here. As you can see that by the time it's reaching around 800, or you can see there is overlap, and the autocorrelations values are large. So it might be indicating the X marginal from the trace plots might be indicated, well, it is converging, there is a lot of overlap going on, so maybe it is reaching stationarity. But when you come to the Y marginal trace plots, you see that the 2 chains is quite separated from the other 2 chains, which is basically saying that the Markov chain has not converged yet. Now, I consider another case where instead of starting the chains at different modes, now I start the 4 chains at the same mode. Now you can see from the test plots that there is a lot of overlap. There is a lot of overlap, and that might falsely indicate convergence. So the these empirical convergence diagnostics may fail to indicate non-convergence to the stationarity in this type of multimodal problems when the chains are not run long enough to visit these different modes. So in the paper we have discussed about what about R hat, and you can see that the other empirical diagnostics measures also falsely detect convergence, or rather fail to indicate non-convergence. And the reason is we are solely depending on the the MCMC chains to diagnose convergence. So it might fool into thinking that they get fooled into thinking that it's a unimodal density. So unless the chains are run long enough to visit the other modes, there might be this problem. So here is my summary from this talk, that so we discussed these two different convergence, these two notions of convergence, which is the convergence to the stationarity and convergence of the summary statistics, how they are related to these questions of where to start collecting samples and when to stop the simulations. We reviewed different popular diagnostics for MCMC convergence, and through some examples, we demonstrated that empirical diagnostics may prematurely terminate the simulations. And in the presence of multiple modes, if the chains are not run long enough, empirical diagnostics may fail to detect the non-convergence. So, but in the review paper, we discussed some other convergence diagnostic measures, empirical convergence diagnostic measures, for example, based on kernel density estimates, where we can show that even in this last situation, the 6-modal example, they're able to even when all the chains are started at the same mode, they're able to detect non-convergence. So not everything bad news. So there are success stories also. So here I stop talk. Again, thank you for listening to the talk. Thank you so much.